Welcome back. In this video we talk about the 4 problems of introductory applied linear algebra. Let's get started. First problem that we're going to speak about is the matrix vector multiplication problem. In this problem, the solution that we search for is the product between a given matrix and a given vector. We can state this problem as follows. Given a matrix A with real entries having m rows and n columns, and given a vector x that has real entries, n rows, and 1 column, we want to find an unknown vector b that has m rows and 1 column, such that A multiplied by the vector x produces the matrix vector product B. As we'll see, identifying dimensions between matrices and vectors, products, inner products, this is a major theme in linear algebra. Though we've specified the dimensions of each of those in the problem statement, I find it very helpful to write it in the actual equation that defines the problem. So here, A was an m by n matrix. It had m rows and n columns. X was an n by 1 vector. And B was an m by 1 vector. As we'll see throughout linear algebra, when multiplying a matrix by a vector, the inner dimensions must agree. Here, the inner dimensions are n, those cancel out, and we're left with an m by 1, which are the outer dimensions of the product. In matrix vector multiplication, we learn how to execute, how to calculate this product. Next problem that we're going to try to solve is known as the linear systems problem. This is the inverse problem of the matrix vector multiplication problem. In other words, we start with a matrix with the same size as before, but instead of beginning with the vector x, we instead are given the vector b. In the linear systems problem, we are asked to find the vector x that produces b under matrix vector multiplication with A. In other words, we'll say we're looking for x such that when you multiply x by A, you produce b. Just as we did before, I find it very helpful to actually explicitly write the dimensions of each of my vector or matrix quantities in the equation. So here, A was an m by n. The unknown vector x is going to be an n by 1 because the inner dimensions must agree. And on this side, B must be an m by 1. Quick comment about color coding. I will write in red the unknown and desired quantity for each of the problem's types, just what we've done in these 2 problems. Notice, linear systems problem, we're given the output and the matrix, and we're trying to find which input vector produces this image under matrix multiplication. That's the opposite of this one. Here, we're given the matrix A and input x, and we're asked which output does this product go to. Next problem we're going to think about is the least squares problem. This problem is directly related to both of these. Here we begin with a matrix A, m rows and n columns, and a vector B, which has m rows and 1 columns, very similar to the start of the linear systems problem. And we want to find a vector x with n rows and 1 columns such that we minimize the 2 norm of the residual vector b minus a times x. And this is measured in the 2 norm. And we'll talk more about that notation as time goes on. This minimum is taken over all possible input values x in Rn. Just as we did in the problems above, let's specifically identify the sizes of each of these vector and matrix quantities. Here, b was an m by 1, a was an m by n. Of course, because this is n, the dimension of x, the row dimension of x, must be n, and here we're talking about a vector by 1, because we're subtracting an m by 1, and then this product is an m by 1. Notice that the beginning part of the least squares problem is identical to the beginning part of the linear systems problem. Notice also that in all 3 cases, we start with a matrix A. The last problem that we talk about in introductory applied linear algebra is something known as the eigenvalue eigenvector problem. And this problem looks as follows. Given a real matrix, in other words, a matrix with real coefficients, with special structure, it's actually a square matrix, meaning that the number of rows equals the number of columns. In the case of the eigenvalue eigenvector problem, we are to find a scalar lambda and vector x such that A multiplied by our unknown and desired vector, this is known as an eigenvector, is equal to lambda multiplied by x. Here we can figure out what size these should be by looking at the equations. A was a square matrix, an n by n square matrix. X was a vector, and we know that the inner dimensions must agree, so here this must be an n by 1. Lambda's a scalar, and then here this is the same x, so this must be an n by 1. With the eigenvalue eigenvector problem, we're searching for an x such that when we hit A with x under matrix vector multiplication, we produce x multiplied by some scalar. The last comment I want to make is this word is very dangerous in math. When we talk about problems in linear algebra, we're going to assume that we have access to information in the form of a matrix and a vector. However, for most people on Earth, it is very uncommon for us to find matrices randomly in life. The reality of producing matrices is actually a very beautiful and difficult thing to do. We'll talk about examples of how to create matrices from real-world modeling problems. Strictly speaking, when we talk about these problems, each of these assume that we start with the matrices. And that's where we'll start our discussion of the techniques of applied linear algebra. Thank you so much. See you in the next video.